is this concept of graphical addition of vectors, which sounds horrible. But if you were to say, hey, what's one of the most important skill sets kids have to have coming out of physics, this would be it. Because we're going to use this concept with anything that's a vector quantity. Displacement, velocity, acceleration of forces, momentum. In the spring, when we get into magnetic fields, we're going to use vectors. When we deal with electric fields, we're going to use vectors. We're going to deal with optics, we're going to use vectors. Okay? So this is a skill set. This isn't, oh, we're going to do this today and then never worry about it the rest of the time. This is something we're going to use again and again and again and again and again. So here's the story. So to make sure everybody's operating on the same page, when you do the graphical addition of vectors, there's certain parameters. Now, today we're just going to do the graphical side of it. Tomorrow we'll get into using trig functions. But the reason that I do the graphical first is because if I don't do that, the trig functions are a train wreck. So one year I was pressed for time because we had some snow days. And I tried to skip the graphical side of it and went straight to the trig functions. Absolute train wreck. Okay, kids didn't get it because they didn't understand the basis of what we were doing. So here's your procedures, okay? They're operating parameters. When you look at an x and y coordinate system, that positive x-axis, that's going to be defined as 0 degrees. That way everybody's working off of the same initial point. Okay, that's going to be 0 degrees. And everything coming around like this in a counterclockwise direction is how we're going to measure the angles. So if I say, hey, I'm at 120 degrees, I'm going to measure around here to 120. If I'm down here, that might be like 250 degrees. If I'm in this fourth quadrant, that might be like 350 degrees. You're never going to have a negative angle. So if you're here in this fourth quadrant, don't tell me, oh, that's -10. I have no idea what -10 means. I do not know. That is no reference. 350 degrees, that's something I can deal with. Okay, so you're never going to have negative angles. And this will play out once you get into the assignment, if you see a negative in front of it, like let's say you have negative b, and b is at say 45 degrees. So if you have a negative in front of it, instead of drawing it at 45 degrees, you're going to draw it 180 degrees opposite, okay? So that would be literally, you just flip it around 180 degrees. If there's a multiplier in front of it, like 2. So if I said, hey, we're going to draw vector 2b, that just means draw vector b twice as long as vector b is by itself. If it was 1/2 b, it would be half that length, okay? Cool with that. Now, this is one of those deals that you understand how to do it. I just have to convince you that you understand how to do this process. So here's the drill. We're going to do a tug of war, okay? So Luke is going to pull with a force of 10 newtons at 0 degrees, okay? Now, these are vector quantities. So what are the two things that it has to have? Magnitude and direction. If I just tell you that Luke pulled at 10 newtons, cool. It's not enough information. I don't know which direction that he's pulling. Is it at 0? Is it at 90? Is it 350? I don't know. Same thing is true if I just said, hey, Luke is pulling at 0 degrees. Great, I have the angle. I don't know how much force he's pulling with. So I've got to have the combination of both things, okay? So Luke is pulling 10 newtons at 0 degrees. Now, Chloe is pulling this way at 8 newtons at 100 180 degrees, okay? So it's close. Luke is pulling at 10 newtons. Chloe is pulling at 8 newtons at 180 degrees. Now, drawn like this, and we're going to do diagrams like this a lot. This is what's known as a free body diagram. This is not tip to tail, okay? Free body diagram, you show all the forces acting from the middle. It's great because it shows you what's going to happen, but this is not the tip to tail method. We're going to draw a lot of free body diagrams, okay? We're going to draw a lot of them. If you want to go into engineering, you're probably going to take a class called statics, which is 18 weeks of doing nothing but analyzing vector diagrams and loads and things like that. So, as a free body diagram, you treat the object as a point and you draw all the forces that are acting from it. This is not the tip to tail method. This just gives us a visual about what's happening. Now, to actually do this tip to tail method,
What's up? How you doing? I'm doing good.
I really didn't ask.
Oh, thanks.
God,
You're welcome. Okay, Chuck,
Shock.
I'm a physics teacher on the edge.
What?
Of what?
Shut the fuck in.
My voice is dying,
Oh.
okay? So the first thing that I'm gonna do, and it doesn't make any difference which one you draw, I'm gonna draw Luke's vector first. So here's force Luke, 10 newtons at 0 degrees. You always at least want to put what the force is. You don't necessarily have to put the 10 newtons at 0 degrees. Would you stop? Just stop moving. It's annoying.
Ain't that your snack?
No, that's my job. Now, from the end of this is why it's called the tip to tail method. So now I'm going to take the vector that represents what Chloe's doing, and I'm going to draw it back like this. So here's force Chloe. 8 newtons at 180 degrees. Now, Charles, who's going to win?
The person pulling 10 newtons.
By how much? Do not make this difficult.
2 newtons.
2 newtons.
Oh, I didn't. I thought you meant time.
No.
What? Can I smack him now?
No.
I thought you meant like in the time. Like, you know what?
There's no time.
Well, that's why I was confused.
Okay. 2 newtons at what angle? 0 degrees or 180?
0.
Okay, you just do the graphical addition of tip to tail.
Sweet.
So, what you're after is what's called the resultant, okay? The resultant is the net effect of the vectors that are acting. Could be 2, could be 3, could be a dozen, doesn't make any difference. So, you do what's called the roux. It's an Australian term, like kangaroo. So R is the resultant. Crikey. And then O is the origin. And this is out. So the kangaroo, the roux, shows you the net effect of what's happening. So I'm going to come in here and I'm going to draw a resultant from that origin and out. Now, if you just tell me the resultant is 2 newtons, is that enough information, Andrew?
Absolutely not.
Why not?
It does not give a direction.
That's right. If I just say it's 2 newtons, cool, great. Doesn't tell me which direction. Now, this is why it's the root, why you draw it from the origin out. Because if I draw the resultant from here back to the origin, that would be 2 newtons at 180 degrees. That would be like saying Luke's pulling this way with 10, Chloe's pulling this way at 8, but we're actually going to go in Chloe's direction. even though she's applying a little bit less force, okay? Doesn't make any sense. That's why you draw from the origin out. Now, here's the other way that you can view this, okay? Some people like an analogy of like walking, all right? So, Luke starts here, and he's going to take 10 steps, 0 degrees. He's going to stop. He's going to walk backwards for 8 steps. He's going to be here. So what this tells me is where Alan has to go to get to Luke. It's like Luke's going, man, hey, I forgot my calculator. Help me out. So Alan, to get to where Luke is going to take 2 steps at 0 degrees. So Luke could have gone for miles and walked back miles. Doesn't make a difference. This is the net effect of these two. Okay? Got 10, you got 8. Here's the net effect. Okay? Well, cool. That's as simple as it gets. Now, a little bit more complicated. Here's the soccer ball.
You got Thatcher?
Yeah, Thatcher.
So for you.
Sydney's going to kick the ball with 10 newtons at, now let's make that 20, at 0 degrees. At the same time, Thatcher's going to kick the ball
Like 5.
with 15 newtons at 90 degrees. Okay? So, Sydney's going to kick the ball this way. At the same time, Thatcher's going to kick the ball this way. Thatcher, where's the ball going to go?
Diagonal.
Up like this. Closer to Sydney, closer to you.
Closer to me.
No, you kick it weaker.
Yeah. So it doesn't go as far, right?
So it's going to go closer to Sydney because she's kicking
Oh,
with 20
closer to
newtons.
like.
The angle,
Oh, yeah.
right?
I thought you meant like where it landed.
No. So this is just in terms of forces.
Yeah.
Okay? Now again, this is not the tip-to-tail method. This is a free body diagram. It just says, hey, this is what's happening. Sydney's kicking the ball this way, Thatcher's kicking the ball this way. Ball is going to go somewhere in between. So I know when I get this angle, it has to be somewhere between 0 and 90, probably closer to 0 because Sydney's force is a little bit bigger. Okay? Makes sense? Now, to actually do the tip-to-tail method, I'm going to draw Sydney's first, 20 newtons at 0 degrees. Now, from the end of this, then I'm going to draw Thatcher's, which is going to be 15 newtons at 90 degrees. When you draw the resultant, you are going to take a ruler, and you're actually going to draw this line, okay? And draw this line. Conveniently, I have this option on here. I'm going to go doink, okay? That's what you're going to draw. Now, when you measure the angle, okay, the second part of this is that you have to measure the angle. So, you're going to take it this way, you have to have a protractor and a ruler. So then, I'm going to take this, and I'm going to measure around here to get like 22 degrees. So, I'm going to measure this length. Let's say that that's 24.3 newtons. And then at 22 degrees, whatever that is. Okay? When you measure that angle, it has to be relative to that positive x-axis where you started. Again, if you like the walking analogy, Connor M starts here, he walks 20 steps. He turns, he walks here. And this point is right here. What we're doing here is telling Connor A which direction he has to walk to get to where Connor M stopped. Okay? Got that?
Yeah.
Third one, which is about as complicated as it gets. Soccer ball analogy. So, Andrew is gonna kick the ball this way. 20 newtons at, I don't know, 40 degrees. At the same time, Mac is gonna kick the ball this way with a force of 15 newtons at 120 degrees. Okay? So, Andrew's kicking the ball this way,
What?
Mac's kicking the ball this way. Where's the ball gonna go?
Somewhere around.
Okay, let's get a little bit more specific than somewhere around that way.
You got
Good.
closer
Yeah, between
to
40 and
the-
90 degrees.
Closer to 40 or
Closer to
closer to
40.
120?
Closer to 40,
Why?
because the force is greater at 40
Okay.
than the force.
So you know the ball is gonna go somewhere in between. So you know when you get this angle, if you get an angle less than 40, you've done something wrong. If you get an angle more than 120, you've done something wrong. Okay? It's the exact same process. So what you're gonna do, so you gotta draw an X and Y coordinate system. Now, none of these are at right angles to each other. So, you're gonna take your protractor, put this on here, and you're gonna measure to 40 degrees. You're gonna make that mark. And I'm gonna draw that line out like this. So, I'm gonna draw this at 40 degrees. So that's gonna be 20 newtons at 40 degrees. Now, here's the story. This is the most critical thing. When I draw max force, that becomes a whole new X and Y coordinate system. It's like you're starting over from scratch. All that does is tell you where this vector ends. So when I draw that 120 degrees, I'm gonna take it from here, and it's just like a whole new X and Y system. So I'm gonna go here, I'm gonna measure around 120 degrees, and draw that line up like this, okay? Don't measure the 120 degrees from that vector. You have to draw it from a whole new X and Y coordinate system, okay? So, I'm gonna come in here, I'm gonna draw this line. Wanted, why won't you draw? Go.
What if your point's not exactly what
Okay,
system is?
there's force Mac, 15 newtons at
What?
120.
Just cheap.
Now, when I draw the resultant, I'm gonna go back to where I started. And then I'm gonna draw the line from that point out. So, I'm gonna come in here, and I'm gonna draw this. Like so. Now, when you draw the angle that you have to give, that disappeared, is from this initial positive x-axis. I don't want the angle in here. That's not what I want. The angle has to be back from this initial positive x-axis. So I'm going to come in here, put my protractor like this. That's going to be 54 degrees. So that might be 23.5 newtons at 53 degrees. And again, if you like the walking analogy, okay? Deacon started here, he walked to here, he's gonna turn, at this point, Deacon is right here. What I'm telling is how Alex is gonna get from here out to where Deacon stopped, okay? And I'm gonna measure from that initial positive x-axis. Cool, got it. Sucks trying to teach without a voice.
Yeah, I know.
What?
Trying to find anything cheaper.
That was. See, no.
7 years.
No, Mr.
I will say murder.
What? The angle? I don't know what how do you retractor?
Hold on.
Because they're not going in opposite directions, so you'd add the forces. Well, kind of way. No, you don't
Okay.
put them together, but.
So up here at the top is the summary of everything that we just talked about. Okay, that's all this is up here at the top. So initially, we're going to deal with nothing but displacement vectors, eventually deal with forces and everything else. So what you have here are 5 vectors, A, B, C, D, and E. The first thing that I want you to do, not on this paper, is on another sheet of paper, so that you get a feel for where these are. You're going to draw out these vectors. If you want to draw them all from the same center, you can. If you want to draw them separately, I don't care. So you got vector A. So you're just going to come out here and you're going to draw a line 5 centimeters long at 0 degrees. Now, word of advice. When you draw this line to be 5 centimeters, you have to put an arrow on it. But don't put the arrow on the end of the 5 centimeters line, because then it's going to be longer than 5 centimeters. Okay? So draw it at 5 centimeters and then put that arrow so that it doesn't extend it beyond that. So then you got vector B, 3 centimeters at 90. Now D is a little sketchy. Okay? Because D is 6 centimeters at 250. Now, your protractors don't measure to 250 degrees. They only go to 180. So, how are you going to handle vector B? Yeah, so this gets you to 180. You need 250, so what are you going to measure? 70. So I'm going to come out here and I'm going to measure 70 degrees, make that mark, and then I'm going to draw it down like that. So literally, these are the 5 easiest points you're ever going to get. All you have to do is draw the vectors. And again, if you want to draw them all from the same common center, you can. If you want to draw them separately, I care not. Just label them so I know what they are. Okay? Now, when you get down to number 2, draw the following, 2B. So how are you going to draw 2B? Now you're just going to draw B, but then you're going to double the length of it. That's it. You got -1/2 A. So what are you going to do with that? Flip it the other way and make it half as long. There you go. Not a big deal. Now, when you get to number 3, okay, I'm going to show you exactly how I want number 3 done. Again, on another sheet of paper, graph paper, plain paper, whatever works for you. So in number 3, you're going to draw vector B. Okay, 3 centimeters and 90 degrees, straight up, measure it. Do not, and you cannot count like squares on the paper and go, oh, I'm going to count 3 squares and call that 3 centimeters. You actually have to measure that out. Now, from the end of this, I'm going to measure around 250 degrees, and then I'm going to draw vector D. So that's going to be vector D. So this is 250 degrees. Okay, so I'm going to draw vector B. From the end of that, I'm going to draw vector D. Cool, got it. Okay? The tricky part is going to be the resultant. So when I draw that resultant, I have to come back to where it started, back to that initial origin. Then I'm going to come in here and I'm going to draw that line from this point out to the end of D. So when I give that angle, I have to measure it around like this. So I can measure this angle and I get 40 degrees. So if this is 40 degrees, but can I list it at 40 degrees? No. Because if you tell me it's 40 degrees, where do I think that's gonna go? Yeah, if you tell me 40 degrees, I think that same thing is somewhere up there. This is 40, but what am I gonna have to do?
Add the 180.
You get like 220. So you're gonna measure the length of this line, give that angle. Luke,
Did you also say negative 40?
There's no negative angles.
Wait, but then how can we make negative?
the negative just tells
Could
you
we, what
to
if we say
drop,
40
you flip
degrees
it over
and
180
negative
degrees.
magnitude on that?
Yes,
So we could do that too.
no.
Okay.
All the, like the up above, that's what I'm telling you. The negative just means you're gonna flip the vector around 100. So if you had negative b would be down here at 180. The negative indicates the direction, it doesn't indicate the angle. Okay, the angles are always, always, always positive. All the negative in front does is tell you to flip it around 180 degrees. Okay? So, what you need to get done by tomorrow is through number 8. Don't worry about number 9. We're gonna deal with number 9 tomorrow.
Oh my God.
Okay? Mr. Hannah, are we okay?
You good,
I
Alan?
almost want to start crying. I'm alright. No, I mean,
You can tear up.
Okay.
Parking. Shut up, Charles.
You need a sharp pencil and a sharp mind. This
And a
is
sharp
all
pencil.
about being neat, okay? Being precise when you draw these measurements.
Nah.
Do not do this. Like, oh, there's B and D. Oh, then I'm gonna draw the next one and that's gonna overlap that. I will flip out, okay? You keep these as completely separate diagrams. You label them. You don't have to write out the numeric values for each one, but at least label every vector so I know what it is, okay? My voice is dying. You're on your own. Yes, Mr.
you
Haney?
mean do 8 or stop at 7?
No, all the way through 8, stop at 9.
Hey, you give me a solid piece of graphic.
If you're not sure if you're doing it right, ask me and I will tell you. Andrew,
Like the spring is